Hello students, welcome to our channel Creative Minds. We are going to start our second lecture on quantum mechanics. Let's get started. First of all, we will try to cover some properties related to the wave nature. We know that all the form of the electromagnetic radiation travels with the speed of the light, following are the properties that are related to the wave nature, wavelength. It is the distance between the two corresponding points on the adjacent waves. Frequency is the number of the cycles that wave undergoes per second, and amplitude is the height of the wave, which is also related to the intensity or brightness of light. Before going into electromagnetic spectrum, we need to know the concept of spectrum. Spectrum is an array of the waves or particles that spread out according to the increasing or decreasing of some property. Electromagnetic spectrum. Electromagnetic radiation includes a range of the wavelengths, and this array of the wavelength is referred to as electromagnetic radiation spectrum. All the waves in electromagnetic spectrum travel at the same speed in vacuum but differ in frequency and wavelength. On the other hand, continuous spectrum is formed by the light radiant energy coming from the sun or from the incandescent lamps. It is composed of the waves in the range of 4000 to 8000 angstrom. How this continuous spectrum is formed? When the beam of the light is passed through the prism, it is refracted or bent to different angles. When received on the screen, they form a continuous band of the colors, which includes violet, indigo, blue, green, yellow, and orange and red color. These series of the bands thus formed is called continuous spectrum. Rainbow is an example of continuous spectrum. On the other hand, the electromagnetic spectrum can be emission spectrum or can be absorption spectrum. Now we will discuss how atomic spectra are formed. When an element in the vapors or in the gaseous state is heated in the flame or in the discharge tube, the atoms are excited and they emit radiation of a characteristic color. The color of the light produced indicates the wavelength emitted of a particular radiation. For example, a Bunsen burner flame is colored yellow by the sodium salt, red by the strontium. In the discharge tube, neon gas glows orange red, helium pink. The device which is used to find out the atomic spectra is called spectroscope, a device in which a beam of the light is passed through a prism and received on a photograph. The spectrum obtained on a photographic plate is found to consist of bright lines. The atomic spectra is actually line spectrum. A line spectrum consists of narrow, dark parallel lines on a brightly colored background produced from a light source surrounded by the cooler gases that absorb and remove certain wavelengths. Line spectrum is of two types: atomic emission spectra and atomic absorption spectra. When the energy is absorbed by the electrons of an atom, electrons move from the lower energy state to the higher energy state. These excited electrons must radiate energy to return to the ground state from the excited state, excited state is actually the unstable state. The emission spectrum is thus formed by the frequency of these emitted light. It comprises colored lines in the spectrum, colored lines which are actually on with a dark background. The type of the photons emitted is helpful in figuring out the kind of the elements the substance is made of, as each element radiates a different amount of the energy and has a unique emission level. Atomic absorption spectra, on the other hand, is constituted by the frequency of the light transmitted with the dark bands when energy is absorbed by the electrons in the ground state to reach the high energy state. The atomic absorption spectra comprises dark lines in the spectrum with a bright background. The wavelength of the light absorbed is helpful in figuring out the number of the substances in the sample. The emission spectrum of the atoms consists of only certain discrete frequencies, which are called the line spectra. Hydrogen, being the lightest element, has the simple atomic spectrum. The atomic spectrum depends upon the electronic distribution in the atom. A detailed analysis of the hydrogen atomic spectrum turned out to be a major step in the elucidation of the electronic structure of atom. The emission spectrum of the hydrogen atom in the visible and near ultraviolet region showing the emission spectra of the hydrogen atom is a line spectrum. Now we are going to discuss some major contributions given by a Swiss scientist John Balmer. For many years, scientists had tried to find out the pattern in the wavelengths or frequencies of the lines in the hydrogen atomic spectrum. In 1885, a Swiss scientist John Balmer showed that a plot of the frequency versus 1 by n square is a linear graph. Balmer showed that the frequencies of the emission lines in the visible region of the spectrum could be described by an equation where frequency is equal to 8.2202 into 10 to the power 14 into 1 minus 4 by n square. This was the equation given by Balmer. First, where n is an integer and it can have any value from 3 to 3, 4, 5 up to infinity. This equation is then rewritten by dividing this equation with c, which is the speed of the light. We got an equation 1 by lambda is equal to mu by c, which is the equation given in terms of wave numbers, equals to 109680 into 1 by 2 square minus 1 by n square. As you can see that the wave number has a unit of per centimeter. Here also n is an integer value and it can have a value from 3, 4, 5 up to infinity. The Balmer series occur in the visible and the near infrared region of the spectrum. Other than Balmer series, several other lines were also found in hydrogen atomic spectrum. This is the table showing the four major lines that make up the hydrogen atomic spectrum, including Lyman, Balmer, Bastian, and Brackett. Lyman series starts from by giving from the integer value 1 and n2 here it can have a value 2, 3, 4 up to infinity, and it occurs in the ultraviolet region, where Balmer series starts by giving n1 equals to 2 and n2 can have a value of 3, 4, 5 up to so on. It occurs in the visible region, where Bastian and Brackett occurs in the near infrared and infrared regions by having n1 equals to 3 and 4. You can see here in this spectrum the Lyman series occurring in the ultraviolet region, Balmer series in the visible region, and Bastian in the infrared region. Balmer formula was only applicable for the Balmer series. So Swiss spectroscopist John Rydberg accounted for all the other lines in the hydrogen atomic spectrum by generalizing the Balmer formula, and he gave his own equation which is known as Rydberg formula, where mu bar is equal to 1 by lambda is equal to 109680 into 1 by n1 square minus 1 by n2 square. Here he generalized the equations as n1 and n2, where n2 is greater than n1. This is called Rydberg formula. 109680, this value is actually the Rydberg constant, which is given by RH. The modern value of Rydberg constant is 109677.57 per centimeter, one of the most accurately known physical constant. This is all from this lecture. We will discuss some other contents of quantum chemistry in our coming lectures.